Hello, I'm Dr. Johansson. I will be the instructor for the science course, Global Climate Change in North America, linked, of course, with Dr. Rosenthal's class on environmental literature in North America. I'm sorry I can't be with you today. I am in Austria at a scientific meeting, presenting results of my research and meeting colleagues, but I will be back next week, and we will actually talk about the syllabus and the assignments and the mechanics of the class at that time when we can have a more interactive lecture and discussion. But this week I want to talk about the basic science of anthropogenic global warming, kind of give you an introduction to some of the basic ideas of the science. And so this is a pretty critical lecture. This particular lecture you will be in the classroom with Dr. Rosenthal because she's going to administer some questionnaires that I need to have answered so I kind of know where you are at, both with the science of climate change as well as in your quantitative abilities. So this lecture you're seeing in a classroom together. The following lecture will be on Canvas, and you can watch it at your convenience, but you need to watch it before next week. So watch it when you can, but don't worry about coming to class next Thursday. So to start off with, I want to talk a little bit about what the elements of the debate are about climate change. It's a sort of a strange thing. We don't debate the function of your kidney or your liver, and we don't debate the law of gravity. We don't debate a lot of things. But somehow people think climate change is controversial, and it's being debated. And it's probably because if we accept the science of climate change, it means that we have to change what we're doing, the way we live, and actually make some decisions that will impact us economically and socially. So that's why it's controversial. The science is really not very controversial. But let's look at the elements. First off, we have prediction. Okay, and so the questions that people have about prediction is the science of meteorology correct in predicting warming with rising CO2? How much warming is actually predicted? And can we trust the models that predict specific amounts of warming? So a lot of the prediction going into the future is based upon models, climate models, and these have been questioned by non-scientists. Secondly, we talk about what has happened so far. This is far less controversial than predicting the future, but still seems to be somewhat controversial with some people. So the questions in this category are, has the climate warmed? Have we had an increase in storm intensity? Have glaciers, ice caps, and sea ice melted? Have there been biological impacts? Have there been economic impacts? And there's lots of other questions that go along with this. Has there been an increase in droughts in some regions? Has there been a movement of invasive species that have been a response to this? Other kinds of things that fit into this category. Third, and this is, to me, the crux of the issue, are the observed changes that we've seen so far in our climate part of natural variation in climate. Okay, where the science is right now and where the debate is right now, there's not very many people arguing that the climate hasn't actually warmed. We have hundreds of thousands, if not millions, of data points of temperature data, and it's not very controversial that it has warmed. That has happened. We've measured it. There's still a few fringe elements that argue it hasn't warmed, but most people accept that it has. Most people accept the carbon dioxide levels have gone up. So the real question becomes, are the observed changes in the climate part of natural variation? Or are they caused anthropogenically? And you should know that word, it means by man. Anthropogenic climate change means we've caused it. It's not natural. And that's where the debate is. Still slightly has some merit. So one question that we have is, has similar warming occurred in the past? So if it's natural now, it means that we should be able to see that it's changed as fast as it's changing now, that it's changed in a similar amount as it's changing now in the past. Okay, and so we ask those kinds of questions. What were the negative consequences of past climate change? And all of this area is the field of paleoclimatology. And paleoclimatology has really become a critical field in recent years. We've developed lots of things called proxies that allow us to reconstruct the Earth's past climates. And so this can be addressed. Also, part of this question about natural variation is, what were the causes of past climate change? Okay, we know there have been ice ages and times when the ice ages, what we call the interglacials, which we're in right now, where it's warmer. We know that in a distant time, such as the time of the dinosaurs, it was actually much warmer than it is today. So the question is, what causes climate change? I mean, worldwide, climate change that it impacts environments and animals and plants that we can detect in the fossil record, that we can detect in the recent record. What are those causes? And are these same causes in evidence today? So you're going to find out, we know what caused the ice ages. So we want to know, are the things that cause the kind of climate change in effect today? We can look at that. And can recent climate change be explained in the absence of the forcing by greenhouse gases? So what this means is, if it's natural variation, we have to be able to explain the climate change using natural causes in the absence of the impact of greenhouse gases. And finally, should we be worried? Some people are at the point where they just say, okay, so it's going to get warmer. I kind of like warmer weather. I don't like winter. Warmer is fine. And this is what some people say. So we have to ask, what are the ecological, sociological, and economic impacts of climate change? And of course, the question we often ask is, will these impacts occur in my lifetime? I think that's an unfair question in part because it's probably not really fair for me to say, well, I've got another 40 years in me. I don't care what happens to my children and my grandchildren. But still, people tend to think of what's going to happen to me in my lifetime. Will these impacts touch me in America? And that's one of the foci of this course. I teach climate change, global climate change on a world scale in my science classes, but we are really focusing on the impacts that are going to be in America because while I hope you are concerned about island nations that are going under the ocean because of sea level rise, or the people of Bangladesh who will experience flooding and terrible loss of life and property, I realize that a lot of you are thinking, will these impacts touch me in America? And that's probably why the debate is in America and not anywhere else. In Europe, no one debates climate change. They all accept it. And the same is true in Asia. The same is true in Africa, South America. We're kind of a lone nation in this. And then, do the costs of climate change exceed the costs of reducing our carbon footprint? So this is the real economic argument, and that is, we know it's going to cost us something financially, economically, to reduce our carbon footprint, to reduce the amount of CO2 we produce. So there's a cost to that. There's a cost to going to wind power and nuclear power and solar power. But do the costs of enduring climate change actually exceed those costs? And what's the time frame for that? Now, if we look at the science of climate change, all evidence collected thus far indicates the planet has warmed significantly. It's about 1.5 degrees Fahrenheit warmer on average globally. Now, it really differs from place to place. So in the Arctic, we've had changes of about 4 degrees Fahrenheit, whereas in Ohio, we haven't experienced that kind of warming. So it's really variable on the planet, but the average is 1.5 degrees. So you may not have experienced it or felt it, and actually because it's so slow, even your parents probably wouldn't notice that it's changed. Um, but it's interesting that 2012 was the warmest year, followed by 2013, which was warmer, followed by 2014, which was warmer. We are now in an area where the climate is climbing, the temperature is climbing. Now, all evidence in science thus far supports the hypothesis that greenhouse gases cause warming, and computer models to forecast future climate are scientifically sound. So we'll look at some of that evidence during the course, but yeah, the computer models seem to be accurate. Now, there is no unifying theory or body of evidence that supports a skeptic or contrarian point of view. We know the planet has warmed. They cannot explain how. And that is the simple truth. They cannot explain in a unified way that scientists would say that's good evidence. They cannot explain how this warming's occurred. And so this is a real important point, this next point. Natural variability is due to natural causes. Okay? Unexplainable warming that occurs in the absence of natural causes is not natural. So some people seem to think that climate will change on a random way. Toss a coin, that's a random kind of change. You know, it'll go up, it'll go down, it's natural. Natural is different from random, okay? Natural variability is due to natural causes. And so you can't just say the climate's changed in the past, so therefore this change we should not be worried about. It changes all the time. It changes in response to causes, okay? And the causes right now, there's a real big finger that can be pointed at carbon dioxide and other greenhouse gases. Now, we could ask, why do scientists buy into this theory? If you started asking about scientists, and we'll talk about the scientific consensus, most scientists, even ones that aren't meteorologists, aren't climate scientists, accept this theory, accept the theory of anthropogenic climate change. And one of the reasons of this is tens of thousands of papers in the peer-reviewed literature from thousands of scientists support the climate change hypothesis. This is not something that 6 people are promoting. This is something thousands of scientists have collected evidence and have published in a literature that is so vast that no one has read it all. No one can read it all. But it's out there, and it exists, and we know it, okay? But we can't get a counter-explanation supported by evidence that's been put forward by the skeptics. They have not got a universal theory of climate change in recent times. They only have taken issue with the minutiae, meaning, oh, this one study might be flawed because of X. Okay, that is easy to do. You can always attack some idea by coming up with some small little thing, and particularly if people don't understand the science to begin with, they can be taken in by this, and that's what they've done. They've argued the little small points that really don't have any impact on the science at all. Now we get to the basic theory. So I've sort of laid out the background of what the debate is, laid out the background of where we are. Hopefully, I mean, I could give you much more on that, but let's start with what is actually going on with this anthropogenic climate change theory. And it comes down to greenhouse gases. Greenhouse gases are mostly transparent to short wavelength energy. So this is visible light and UV light. And this light hits the surface of the Earth. It's kind of an interesting idea. You don't realize this, but when you look up at the sky, the light that's coming down, the radiation that's coming down, is almost all visible light, as well as the shorter wavelengths like UV light and X-rays and some of those kinds of things. Okay, this light hits the surface of the earth or the surface of your skin and is absorbed. It can either be reflected out, so if it hits some ice or something very light colored, a lot of the light will just reflect back into space and go right back into space. Okay, but if a surface is not white or a mirror, and even if it's white, some of that light energy will be absorbed by the surface. Maybe it's the surface of your skin. And what happens then is that light energy is converted into heat energy. And then if a body is hot, like we're always hopefully a little bit warmer than the surrounding air. We'll be uncomfortable if we aren't. But if our bodies are warm, they actually radiate heat. So that if you had infrared goggles on, you go, oh, that person is lit up like a Christmas tree. Okay, and that's true of all the surfaces on Earth. Okay, a blacktop parking lot, we know how much that heats up. But even things like trees, houses, tops, fields, ocean water, everything radiates heat. And this heat goes back into space. It doesn't have much light in it. The light would go right back out into space. But these long wave energies, these infrared and heat, get trapped by greenhouse gases. Now, what are the greenhouse gases? This is a table that I kind of like. It shows some of the major atmospheric gases, which are nitrogen, oxygen, and water. And you can see the fraction is 0.78, so 78% nitrogen, 21% oxygen, and 2% water, 0 to 2%. It varies depending on where you're at. Okay, so, and we're missing some in there. Argon is actually the thing that's missing, but who cares about argon? Now, then these gases down at the bottom are actually considered trace gases. So CO2 is the most abundant of these. And what you can see is 388 parts per million. Actually, I should change that to 400 parts per million. But you can see the fraction of it in the parentheses there, 0.000388. That's the fraction, or 0.4%, because it's 400 parts per million now. 0.4%. It's a trace gas. Okay, not very much of it's in the air, but it's enough to make a difference. And then you can see some of these others are even smaller amounts, except for ozone, which is highly variable. Ozone develops in our air as part of the development of smog. So in some areas where there's lots of cars, ozone can be quite high, and in other areas it's quite low. It's not uniformly distributed. But these are all the greenhouse gases. The 5 that you see down there are the greenhouse gases. Now, this is a diagram of the atmosphere layers, and if you're in earth science, we talk about all these layers. We're only going to talk about 2. Okay. The most important one to us is the troposphere. Troposphere is where we live. That's the bottom layer, and it is characterized several ways. But in the troposphere, it gets colder as you go up in altitude. And you all know this. If you go up in the mountains, it's cooler than it is down here. If you go up in an airplane and look, if you've ever been on an intercontinental flight and you see the temperature outside, it's like a chilly, minus 49 degrees Celsius or something. That's because you're up near what is called the tropopause, which is the place where the troposphere ends and the stratosphere starts. And the stratosphere is defined by the fact that it warms as you go up. So you're warming up through the stratosphere to minus 3 degrees C. That's a balmy 27 degrees Fahrenheit. Okay, you could handle that in a coat, except you wouldn't be able to breathe up there. But apart from that, it's fairly warm. Now, the other layers we're not going to worry about, but the stratosphere and the troposphere are important because the troposphere contains 85 to 90% of the mass of the atmosphere, and it warms by convection from a warm Earth. So the reason the atmosphere is warm and not frozen is because heat is re-radiated after the light is absorbed, and that warms the atmosphere, the troposphere. Now, if radiation from Earth is trapped, it warms more. So one of the critical things about the troposphere is we have these greenhouse gases, and they trap the heat going out and then re-radiate that heat back towards the Earth. Now, cold air on top of warm air is unstable, so the troposphere constantly mixes. What that means is we have wind down here. We have weather. Fronts come in, fronts leave, wind blows. We have the buildup of these stratocumulus clouds. All of this stuff is going on in the troposphere because it's unstable to have cold air on top of warm air. Cold air is denser. Now, once you get to the stratosphere, this is warmed primarily based on solar UV radiation and ozone trapping the heat. So the closer to the sun we are, actually the warmer it is because that's where more UV light is, and the ozone traps it and re-radiates it as heat, and so we get this you're hot higher up because you're closer to the sun. Now the stratosphere is very stable. There's no turnover, but it has fierce winds. So the jet stream is up in the stratosphere, and the stratosphere has been cooling recently. Now this is kind of interesting because the fact that the stratosphere is cooling is actually evidence of climate change due to greenhouse gases. It's one of the key elements of the proof, because what's happening is the stratosphere is warmed from the top by the sun. It's warmed from the bottom by radiation coming up from the Earth, and then that radiation is trapped by the ozone up there and CO2 and other things, and so the stratosphere has been cooling. And you might say, well, why is that? It's because the troposphere is trapping the radiation that would otherwise come out because of the greenhouse gases that have increased. So it's not cooling at the top, it's cooling at the bottom. Now, I'd like to talk a little bit about the climate pioneers. These are people that are fairly famous in developing the theory of anthropogenic climate change. And I also like to do this because I want you to understand that the science of climate change is old, okay? It's been understood for a really long time, and it was never very controversial, okay? It wasn't scientifically controversial. Now, Jean-Baptiste Fourier, very famous physicist, proposed the greenhouse effect in 1827. So this is when we first get it. And he asked a couple of questions. He said, why doesn't the Earth just keep heating up until it's hot as the sun itself? If we have this light coming from the sun, it's hitting us. Where does that heat go? Why aren't we really, 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 really hot? Because what that means is if we're not really, really hot, the heat is escaping. And then he said, well, if the heat can go back into space, why isn't the Earth an ice block? Why doesn't all the heat just go out? And so what he said was, when the heat is re-radiated, some of it is trapped. And he said it's just like a greenhouse, because they understood greenhouses. You put glass, and that's exactly what happens. Light comes through, the heat can't get out. So he said that the atmosphere acted like a greenhouse. Now, he didn't know what exactly was causing this in the atmosphere, and that was figured out by John Tyndall, another famous physicist. He tested a number of gases' ability to absorb infrared light, and he discovered that infrared was absorbed by CO2 and water vapor. Now, he didn't figure out methane, he didn't test some of the other greenhouse gases, but he figured out carbon dioxide and water vapor, and that was done in 1860. Now, the one that really started the predictions going was Svante Arrhenius. So in 1896, and he later won the Nobel Prize for some other things, so this is actually a very famous chemist and physicist. But he estimated that a doubling of CO2 would increase the global temperature by 5 to 6 degrees Celsius. He thought a change in CO2 could explain the ice ages. He was mostly wrong. Okay, and he speculated at the levels of coal burning during his lifetime that CO2 would double in 3,000 years. Now, we've been very, very busy, and we're producing a lot more CO2 than that. So now we expect it to double sometime in the next 50 years. Okay, but what's interesting, this amount of warming with doubling that he predicted, 5 to 6 degrees Celsius, currently the best scientific estimate is that with a doubling in CO2 from pre-industrial levels, we'll get a warming of 4 to 5 degrees Celsius. So this guy, with a slide rule and a pad of paper, figured out pretty closely with his primitive models what the warming would be with the CO2 from burning fossil fuels. Very prescient study. Now, he actually liked the idea of climate change because he lived in Sweden and he thought it would be nice to be in a warmer Sweden. Okay. And there were a lot of people back then that thought, oh, warming, that's okay. Okay. We'll find out why it's not. Now, Guy Callender was an engineer, and he proposed the Earth was warming due to anthropogenic CO2 increase from burning fossil fuels. In 1938, he wrote his paper, and he determined the background concentration of CO2, and he detected increases in the background. So he said, the climate is warming already due to excess CO2 from burning fossil fuels, and he said it in 1938. Now, his work was ignored. One of the reasons was he wasn't a professor. He was an engineer. He worked for, some companies, and so he had restrictions on what he could release in his data, and so they didn't accept his work. And then also we went into this strange cooling period in the 1950s and 60s, due primarily to the aerosol effect. And so people forgot his work. But when the climate started warming in the 70s, it was called the Callender effect. It wasn't called global climate change. Now, the one pioneer of all of these that you may have heard of is Charles David Keeling. This was the guy who, as a graduate student, started measuring global CO2 levels from the top of Mauna Loa. He started this in 1958, and it was not hard to connect the dots. This is the carbon dioxide levels at Mauna Loa. And so this early period, he actually was personally responsible for this curve for about 30 years. Now, since then, it's finally been funded. It's funded by NOAA, he tells a story of how he had to continually seek funding to do this because people thought, well, it's not that important. But what you can see is this red line. That's the carbon dioxide going up, and the reason it's a jagged line is every one of the peaks is a higher CO2 period of time. That's the end of winter, and then the trees in the northern hemisphere leaf out in springtime. They photosynthesize, they pull the CO2 out of the air, and it drops down, and then it will go back up. So in Hawaii, what's cool is it's a little island out in the middle of the ocean, so a lot of the variability in climate, you don't see it. So this is really the hemispheric breathing of the plant life that we have. And so he saw that, but he also saw within 3 years that the CO2 was going up. And you can see it's been very, very steady. Now, I want you to think for a minute. So some people have tried to say that the CO2 has gone up due to other causes, such as volcanoes or excess forest fires, because these both produce CO2. Look at the graph and think about, does that look like it's caused by volcanoes or unusual forest fires? No, it doesn't. If it was a volcano, it would be a high peak. And we actually have, during this period of time, had some major volcanic eruptions. They don't show up. Okay, they're not the source of the CO2. It's from burning of fossil fuels. Oops, sorry. And then finally, here's a guy that was not appreciated or understood for a long time. This is Milutin Milankovitch, and he identified 3 principal cycles that drive the Earth's global climate and explain the ice ages. So he figured this out. I'll talk about him a little bit later because it's pretty cool. But based on these cycles, Earth is now in a cooling cycle. So this is very important. If you said, naturally, what should our climate be doing right now? You'd say, naturally, the climate should be cooling very, very slowly. That would be natural. So let's look at the fundamental things. So we had this carbon dioxide. I mean, Svante Arrhenius understood this. Tyndall understood this. Callendar understood this. Keeling understood this. So it's been known for a long time. Let's look at what's happening. Now, the main thing in this diagram to look at is that the incoming solar radiation is about 342 watts per meter squared. So the sun is pretty constant. It does vary a little bit in its output, but this is an average, and it's pretty close to what we always get. So this amount comes in as light and UV, as I've said, short wavelength radiation, and several things can happen to it. There's a little bit that's absorbed by the atmosphere. There's a little bit that's absorbed by the surface, about 168 of those watts. And then there's some that's just reflected into space. You can see that 77 watts worth of the energy are reflected by clouds and aerosols in the atmosphere. About 30% is reflected by the surface. So if it's ice or snow or even light-colored surfaces of some sort, it can be reflected back into space. So we have in this diagram, in that big yellow thing, 342 watts coming in and 107 going out without really having an impact on anything. Okay, they just are reflected back into space. You see these nice pictures of the Earth glowing blue and white. Well, that's what we're seeing. Okay. Now, once the light is absorbed by the surface, then that surface warms and you get surface radiation. So if we go over to the major pink thing going up, we've got our surface radiation coming off. Some of that is reflected by clouds and comes back. Some of it makes it into space as heat, just goes out into space. But some of that heat hits greenhouse gases, and the greenhouse gases absorb the heat radiation, and then they re-radiate it. And it can come off in any direction from a gas molecule, but if it comes back towards Earth, it's back radiation, and it will warm the atmosphere, and it will come back and actually warm the surface, and so we have some of this heat that's trapped. You'll notice that the outgoing radiation is 235 watts per meter squared. Okay, that's exactly what 342 minus 107 is. Okay, so this is a diagram showing the Earth in balance, where as much energy comes in, also goes out, and so we maintain an equilibrium of about 15 degrees Celsius in this scenario. Now, this is a diagram that shows what can happen with this. If you look at the column in A, they're using 240 as the number. So 240 watts comes from the sun, 240 watts leaves from the Earth's surface, and that will actually give us a temperature of about 15 degrees Celsius on average. Now, if we change this, so now you can see we're still, in all of these, you're getting 240 from the sun because that doesn't change. But let's say we have greenhouse gases in the atmosphere, and so not all the heat makes it out. It's about 4 watts that doesn't make it out. per meter squared. With a doubling of CO2, this is actually predicted. And if we do that, we get an imbalance at the troposphere stratosphere level, and what will happen is that will trap heat in the lower surface until there's so much heat below that it's radiated and it punches through those greenhouse gases. But that's going to give about a 1.2 degrees Celsius increase in temperature, or about, I don't know, 2 degrees Fahrenheit. So we can have this kind of warming with just the CO2. Now, if CO2 was the only greenhouse gas and there were no feedbacks, that's what we get with the doubling of CO2, and that would be okay. Probably. Most people feel like a 1 degree Celsius change, we can live with that. But it's not what happens. There are these things called feedbacks. And so actually what they're saying, this particular model, is that we get an additional 3 degrees Celsius with the doubling of CO2. That number's actually increased because the importance of feedbacks is now understood better than when this diagram was created. What are the feedbacks? Let's just give you a couple of examples. I'm going to come back to these. But, okay, so let's say, we have a lot of light being reflected by polar ice and sea ice and the ice caps on Antarctica and Greenland and other places, okay? And when light comes in and hits that, it just bounces into space and we don't get heated up. But now the temperature goes up just a tiny bit from the carbon dioxide, and it melts the ice. And now we have a huge area that once was a mirror and is now soaking up the radiation. Well, it's going to heat more, and that is a feedback. Another feedback is polar soils, which are very organic in nature. They start to thaw. It doesn't take much, a little bit. Somewhere on the range, from the North Pole into where, we're here in Cleveland, there's a point where, the soil just barely thaws or doesn't thaw. And now we change that just a little bit. We move north a little bit of how much soil thaws. Now that soil is going to decompose. Now it's going to release methane, and that's a feedback. That's going to warm the climate more, and so we get more warming. So a lot of these things are called positive feedbacks. We'll talk about all of them, but it really is a matter of you get a little bit of heating, you get more heating because of the feedback. Now, radiative forcings. This is a real important thing because this is how climate scientists predict what will happen. So with a doubling of CO2, you get a radiation imbalance of 3.7 watts per meter squared at the top of the troposphere. Now, there are other imbalances that we can consider as possibilities, okay? So this is one. Greenhouse gases cause an imbalance. But here's some other things. So what happens if we change the amount of radiation coming in? What if the sun did get brighter and did send in more radiation? Well, that would cause an imbalance, and because there would be more heat and the temperature would go up. If the sun cooled by some means, then we would cool, okay? So the amount of radiation coming in is important. The amount of radiation going out is the other thing, and that's the thing that we're most concerned about because greenhouse gases stop that. But we can also affect the amount of radiation going out by the albedo of the surface, by how light the surface is and how much it reflects light. Because remember, reflected light goes back into space without heating anything, okay? So, if we change the color of the surface, that's going to influence the amount of radiation going out. And then also, of course, greenhouse gases. They affect the radiation going out by slowing it down. A change in aerosols. Aerosols reflect radiation. And the most important aerosol is sulfur dioxide, which is produced when we burn coal. And the sulfur dioxide actually reflects light out and actually causes cooling. Okay. And then we can have changes in other greenhouse gases. We've got 5 greenhouse gases, which we talked about. They can change. Okay. Now, where is the carbon? This is an important diagram. What you can see is in the atmosphere, we had about 600 billion tons in the atmosphere around 1700, 760 as of 1999, and it's more than that now, but you know, that's a ballpark figure. Look at the soil organic matter. Twice as much carbon as is in the atmosphere, or a little bit more than twice. What that means is if that litter starts decomposing because of warmer temperatures, that's a problem. That's a lot of carbon. Terrestrial living organisms, it's kind of interesting. There is less CO2 or less carbon in all the plants and all the animals living in the ocean and on the actually living on the land than there is in the atmosphere. So that's kind of interesting because it means that if we cut down a whole bunch of trees and they decompose, it will contribute to that top amount. If we plant trees, we can remove some of the CO2 from the atmosphere, but we can't fix the problem just by planting trees. Okay, we can't, you know, double the amount of life on Earth. That's not going to happen. And so we can increase this or affect this in some way, but we can't do anything with it. Now, the ocean is a huge reservoir for carbon dioxide. It's dissolved as carbonic acid. It's in carbonate shells. It's in coccolithophorids. Excuse me. But it's an awful lot of carbon. A lot of the carbon dioxide that gets into the ocean stays there. Most of it does. It can have some of it come out, but most of it stays there, and it's really a sink right now. The ocean is sucking up carbon dioxide, turning it into carbonic acid, and precipitating it as carbonate shells. When this carbon is precipitated, it ends up going into the marine sediments and sedimentary rocks, and then it's just locked up. It's gone. If we could take our excess CO2 and get it, you know, tied up in the calcium carbonate cycle in the ocean and shunt it down to the sediments, we could fix our problem. We haven't figured out how to do that, and probably won't. And then look at fossil fuel deposits. 4,000 to 7,000 billion tons of fossil fuels. If we burnt all of those, we certainly would die before we got it done. Okay, we are not going to change our consumption of fossil fuels because they're running out. There's lots left, and particularly coal is extremely abundant. So, you know, it's a dangerous amount of carbon that's available, and it's scary to people who know just how much fossil fuel there is. Now, let's look at a simplified mass balance. The components of annual global carbon budget for the 1980s and 1990s, we look at these in gigatons. So let's just look at the columns, principally the 1980s and 1990s, because the last column is 2000, 2005. They only had 5-6 years, and that's not really relevant, and we're further along than that anyway now. So let's look at these amounts. So you can see emissions, so how much CO2 we threw into the atmosphere, 5.4 to 6.4. It has continued to increase. Sorry. The atmospheric increase has been much less, though, which means that a lot of the CO2 that's released into the atmosphere does not stay in the atmosphere. Okay? You can see a lot less is there. Now, where does it go? It gets sucked into the ocean. So a lot of the excess CO2 is removed by the ocean, and then there's also some removed by the land. And what you can see is, you know, this is variable, The terrestrial sink, which removes things, so these are the trees pulling the CO2 out. That is a good thing. But land use change, like cutting down the tropical forest and putting in a field of corn, is something that yields CO2. So the land use change almost balances out the effect of the sink of the plants that suck the CO2 out, and so we don't get as much benefit from that as we could. But what you can see is, this balances. And we know with great precision how much CO2 is in the atmosphere, and we know with great precision how much CO2 we put in the atmosphere. And we know this not because we measure the amount of carbon dioxide released from burning fossil fuels or setting cement. It's because fossil fuel and cement are globally traded. And so we know exactly how much tonnage of fossil fuels are sold, and therefore we know how much is burned. Now this is a simplified mass balance showing what has happened over the last 10,000 years. We now emit about 7.8 gigatons per carbon dioxide. Of that, about 60% is reabsorbed in the ocean and terrestrial life, and about 40% remains in the atmosphere. And this is the amount that is driving up the parts per million of CO2. Now, if we look at this graph, this is kind of stunning. So this gives us 10,000 years. And what you can see is, yeah, CO2 went down a little bit, then it went up a little bit. Beginning about the year 5000, started climbing slightly. And then something happened at the beginning of the Industrial Revolution. We started burning coal, and then we started burning oil, and then we started burning natural gas. And so you get this incredible spike in CO2 in the atmosphere. I don't think anybody that's a rational person can look at this graph and say, oh, CO2 hasn't climbed in an exceptional, unprecedented way. It really has shot up. Now, who are the culprits for global fossil carbon emissions? The total is the black line, but the two that are most interesting are the solids, which is coal, blue line, and the liquids, which are that sort of ochre yellow kind of line. And what you can see is early on, it was just coal. That was the first one we burned up until about whatever that time frame is, about 19 something. We rented a car, we started burning gas, and we started using heating oil. And so the liquids take off, and actually at some point surpassed the CO2 from coal, but now coal has surpassed the CO2 from gas and oil. And it's primarily because China and India are building a lot of coal-fired power plants, and other nations of the world are as well, and that's the problem. Okay. Now we can also see gases. That's natural gas or methane. That use has gone up. Cement produces a little bit. Flaring produces a little bit. So you get an idea what's going on. Now, who's doing this? USA. Okay, take a look at the U.S. That's the top purplish line. The world leaders in producing carbon emissions up until just a few years ago when China surpassed us. But to say that, we aren't the primary nation responsible for climate change and for CO2 emissions would not be in accordance with reality. Now, another line that's of some concern is that light blue line. That's India, and that's steadily climbing, and they have no intention of slowing down. They want to make power plants. They want to bring electricity to their people who mostly don't have electricity, and they're going to do it with cheap coal. Now, I've said the ocean acts as a sink. How does it do this? Calcium carbonate formers remove a significant amount of carbon. And one of the most important of these excuse me, are the coccolithophorids in the phytoplankton. That's what this picture down at the bottom is. These are algae, and they precipitate calcium carbonate to make these very attractive shells. They're microscopic, so each one of those is about 5 microns across. But they're very, very abundant, and they precipitate this calcium carbonate, and when they die, they sink. And when they sink, they take all that carbon to the bottom with them. Coral reefs are a significant sink because of calcium carbonate, so coral also fixes calcium carbonate, and so that takes it out of the air as well. And then there is just a simple carbon dioxide will dissolve in seawater. That's a slow process, but seawater can actually hold a lot of calcium carbonate. One of the things that we're concerned with right now is it's absorbing this carbonate, this CO2, and that's acidifying the ocean by making carbonic acid, and that's a concern as well. Now, uptake by the oceans will likely decrease as the water of the ocean warms. There's several things that can happen. We know that during the ice ages there was more biological activity in the oceans, and it was likely due to deeper mixing that occurs in colder water. So when the water's cold, it can mix the surface layer when the wind blows over it better, and so it can bring more nutrients up to the surface, and you can have more productivity. More nutrients were entrapped in the surface water, leading to higher productivity. Now, photosynthesis captures atmospheric carbon in vegetation. So here's a diagram that shows this nice little tree. This is true of all plants, where it takes water and nutrients from the soil and CO2 from the air and puts it together into sugars, organic tissue. Now, oxidation, that means if you have a forest fire or the soil decomposes, or even just metabolism of the tree, returns carbon to the atmosphere. The organic material is destroyed and combusted. Now, one cause for concern is the uptake by terrestrial systems will likely decrease as the planet warms. Less will be sequestered in organic matter in the soils. In areas of drought, plants will take up less. And deforestation reduces the ability of the land to take up carbon dioxide. So there's a number of things about the terrestrial ecosystem that are matters of concern. Now, if all anthropogenic CO2 emissions were halted, it would likely take several hundred years to return to pre-industrial levels. But CO2 emissions are neither declining nor standing still. They are steadily increasing every year. And so this is a big concern. We're getting into a problem that can't fix itself quickly, that we can't fix quickly, and we seem to be able to think that the technology is going to save us in the end when there's no evidence it will. Now, this diagram shows the relative importance of the major human-produced greenhouse gases to current warming. So there's actually 5 of these gases, and what you can see is carbon dioxide provides 56% of the warming effect. Methane 18%, CFCs 13%, ozone 7%, and nitrous oxide 6%. Now, all of these are important, but carbon dioxide and methane are more important. So those are the big players. So let's look at methane. I haven't talked about methane so far. Methane keeps going up. It's been going up for 100 years. And what you can see in this diagram is how it went up over the last 10,000. And you can see that, well, okay, not much happening, and then all of a sudden, enormous happening, okay? And so this is showing our methane levels and a very, very rapid rise. Natural sources of methane exist. Wetlands are the primary source. There's these methanogenic archaea that live in wetlands, and they convert, they're decomposing the stuff in the wetland and releasing methane. Termites and cows also release methane, and cows might be considered not a natural source because we wouldn't have that many cows if we weren't raising them. Now, there are some positive feedbacks with warming. Permafrost melts and decomposes, and it releases methane. Then there's also these things called methane clathrates in the ocean. Excuse me. And hope you're not falling asleep like me. No. Methane clathrates melt in the ocean, and they release methane into the atmosphere, and this is something we worry about. We'll talk about more. Since 1800, methane has doubled. It's unprecedented for the last 6,500 years. This is due to leakage from coal mines, oil, and gas wells. So these mines and wells leak natural gas. Essentially, natural gas is methane. So this leaks from these mines, and we can't do too much about it. Cattle belch, and they belch a lot of methane, and it's actually a significant amount that they belch. And so that's from humans. Rice paddies release methane because, remember I said wetlands were a natural source? Well, rice paddies are wetlands because they flood the fields. And actually, this is the early impact on climate change. They figured that the Anthropocene goes back 8,000 years. It started with rice field culture. Landfill sites also release methane, burning wood and peat, and waste treatment. All these put methane into the atmosphere. Now, nitrous oxide has actually increased by 16% since the start of the industrial age, and this is primarily because of fertilizer. So we apply the fertilizer produced from fossil fuels. So we have to use a lot of fossil fuels to make the fertilizer, which means that we have CO2 in the air. Then when we put this nitrogen fertilizer into the soil, the ammonia is converted to nitrate. Nitrate is then denitrified by bacteria to nitrous oxide, and finally to nitrogen gas. This shows the variability of nitrous oxide over the last 10,000 years. You can see it's a very similar curve. It's really jumped. Now, chlorofluorocarbons, we don't have any natural members of those. This diagram is showing the ozone hole. Okay, and when we made all these refrigerants and aerosols, they destroyed the ozone layer in the stratosphere over Antarctica, and that looks pretty bad. 5% loss of ozone of the ozone column over mid-latitudes. So even right here, we've had some ozone loss from our protecting us from up above, and so that's a problem for us. The Montreal Protocol was put in place when someone reported the ozone hole, reported the problem it was going to be, and said, we need to have a plan for cycling out of CFCs, which are these refrigerants that are important to use. And so all the nations of the earth agreed that if it could be shown that it was the ozone hole was due to CFCs, they would stop making them. And a couple years later, it was proven, and they stopped making them. And this is used as an example of, if the nations of the world want to do something, they can do it. CFCs are the most powerful greenhouse gas. They are 5,000, 10,000 times as effective as CO2. So even though they're really, really trace gases, they're really effective. They're being replaced by hydrochlorofluorocarbons, HCFCs, which break down faster and affect ozone much less. One of the problems with CFCs is they just don't break down. But these break down faster, so there's less catalyst that can be done. Now, breakdown by CFCs reduces the heat trapping at the poles. We actually get a little bit of cooling at the poles because of this. It's produced by oxides of nitrogen, and that's what's the main thing from car smog. And it's produced in the upper atmosphere by jet planes, which release nitrogen oxides. Now, this is the summary of the radiative forcings, and what I want you to see in this diagram is that CO2 is up there at the top. That's a very positive forcing. That's causing a lot of warming. And then you can see methane, nitrous oxide, and halocarbons. More than half the impact of carbon dioxide. Tropospheric ozone, also very important. the stuff that's in the stratosphere actually cools us. So those are some of the main positive ones. Black carbon on snow is there as well. And then you can see the land use, so the surface albedo. We clear the land, and actually, if you remove the forest, which is dark, and replace it by a farmland, which is light, it actually cools things. And then we have the aerosol effect. These are SO2s from coal, and you can see they provide a very significant cooling effect. And so the total net anthropogenic forcing, very, very positive, very, very high. And it's not surprising this is creating an imbalance that has warmed the planet. So I'll let, if Debbie hasn't already given the questionnaires, I'll let her do that. Sorry, Dr. Rosenthal. And so do watch the other lecture that I have put online for you. And I'll see you next week.